Ease provides the capability to plot a dependent variable as a function of two independent variables in what are referred to as three-dimensional or XYZ plots. So Ease can generate different types of 3D plots, including the two that we're going to cover in this section, which are contour plots and also 3D surface plots. So let's discuss these plots in the context of a very simple example function. So z here is a function of x and y, and you can see the formula, and we'll enter that formula into Ease as shown below. You'll notice I used the dollar unit system to specify that the arguments of the sine function will be radians, and for x equals 0 and y equals 1, I get z equals minus 2.621. Right? So all of the 3D plot types require three-dimensional data. In other words, in order to make a plot, I'm going to have to vary both x and y over some range and then plot the values of z as a function of x and y. And these data can either be provided in three-column form or in the form of a 2D table. So here we're going to stick to three-column form, and in this form the data are provided as three separate columns corresponding to the two independent variables and then the dependent variable. So for this problem, we're going to provide the data in three-column form by first generating a parametric table and including in this table the variables x, y, and z. And then in three-column form, the independent variables can be provided in any order. They don't have to be provided on a regular grid, but that's what we'll do here. The first step that Ease is going to do internally is interpolate and extrapolate the data in order to provide a suitable grid. But here, let's go ahead and vary the independent variable x from minus 3 radians to 3 radians in 41 discrete values. And we will vary the independent variable y from minus 5 to 5 also in 41 discrete values. And therefore, 41 times 41 is 1,681, and that's how many rows have to be in this parametric table. So to populate the column containing x, we'll go ahead and right-click on the column header and select Alter Values to obtain this dialog. And then we're going to vary x from minus 3 to 3. And then we're going to repeat that pattern every 41 rows, and that's what's shown here. And then to populate the column containing y, we'll do the same process, but we're going to vary y from minus 5 to 5. In this case, we're going to apply that pattern every 41 rows. So that's what you see here. And what you can see then is that we've covered this entire 2D grid from x equals minus 3 to 3 and from y equals minus 5 to 5 in this kind of a regular pattern. Alright, so now we can make a plot. So the first thing we're going to do is solve the table. So we'll go back to the equations window and comment out the values of x and y that we set, and we'll solve the table. So now we have a value of z at every value of x and y, and we can start to make different kinds of plots. So the first plot is a contour plot, and there's a couple different kinds of these. And so if I select New Plot Window from the Plots menu and an XYZ plot, you can see that I get this plot setup dialog. And one of the selections here is a contour plot. And the contour plot illustrates lines of constant values of the dependent variable, in this case z, so these are isometric lines, in the parameter space defined by the two independent variables. So here we'll just select contour lines from the types of plots, and then we'll specify, their dependent variables are x and y, and our contour variable is z. And you can adjust the minimum and the maximum and the interval of each variable if you'd like. And the data then in the columns will be interpolated or extrapolated by the internal plotting algorithms to provide values of the independent variable over the entire selected range at relatively fine intervals. And we can do that either using radial basis functions, which is what's shown here, or we can switch to biquadratic polynomials. And you can change the grid size by controlling this resolution slider. The smoothing slider isn't typically that useful unless you have experimental data or some very sparse data set where outliers or other kinds of gaps might be present, but normally you would keep this over and set to 0. And when you're ready, then select OK, and you can see that you have a contour plot as shown here. So apparently we have, for this function, sort of islands and holes that sort of alternate as you move along in the x direction. This becomes even clearer if you want to add some color to this plot using the contour bands plot. So we'll go back to the dialog and select contour bands. And in this case, you can see that each contour band is indicated by a color, and you get this legend or this color map over here that tells you what color, what Z value each color represents. And there's different color schemes available. This is called the full spectrum color scheme. It uses all the colors in the rainbow, but you could also use colors only ranging from blue to red or even grayscale. If you want to change the color scheme, you just click the right mouse button anywhere within the plot rectangle, and you will get to the modify plot dialog that lets you do that. The other kind of 3D plot that's handy is a 3D surface plot. So the 3D surface plot again uses these data, but this time instead of creating contours, it'll actually plot the surface. Right? So you'll see a 3D surface, and you can rotate that surface and things like that. So here, let's go ahead and build that. So we just select that plot type, and then you select the dependent and the independent variables, and we'll select 3D surface, and you get this plot shown here, which I can rotate and so forth. There's a toolbar or a control panel down here at the bottom. If it's not visible, just right click anywhere in the plot and it'll appear. And you can do things down here like manipulate the axis or the legend. In other words, the color bar, you can turn it on and off. You can change the position of the grid, the perspective, and there's some other things down here that you can experiment with. This color checkbox here is useful. It has sort of 3 positions that engage with a mouse click, and the 3 possibilities again are sort of black and white, which is no check, blue to red, which is a gray check, and then full spectrum, which is a black complete check. Normally the color that we use for a plot like this is another indicator of what the z-axis variable is. So you can see that here, like the red is where the z variable is high, and then the blue is where it's low. But if you want to, you can actually have the color correspond to a totally different piece of information, in which case you have what is sometimes called a 4-dimensional plot. To demonstrate this capability, let's just assign the color of the plot to another variable c, and we'll just calculate c for every value of x and y as being the distance in the xy plane, the distance from the origin. So c is the square root of x squared plus y squared. And we'll go ahead and add c to the parametric table and resolve the table. And now we'll create a surface plot where the surface itself is z, but the color of that surface will be related to this new variable c. And the way you do that is you just click on this z-axis variable label, and you'll notice it then changes to color variable, and it turns the list box yellow. So here we'll select C to be the variable that's used to specify the color, and we'll click OK. And yeah, now you have a plot where the color is the distance from the origin, and it's totally different than what the value of the z is. If you look at this from the top, so let's just select the top view, you can see very clearly that the color is the distance from the origin. And of course you can do all kinds of things with this as you have different types of data that you're trying to visualize.